So in this video, we will try to understand velocity and acceleration analysis of single slider crank mechanism using analytical method. Now, as shown over here, we are having the position of the crank coinciding with inner dead center, and as the crank starts moving from the inner dead center position, then as you can see over here, as the crank starts rotating from this particular point and it has covered the angle theta and it reaches to this particular position, this is the angle theta from the IDC position, then the piston has moved from this position to this position. So this is the displacement of the piston. So we have to find out what will be the displacement of the piston when the crank has turned an angle of theta from the IDC position. Once you get this particular value, then you can easily differentiate that displacement with respect to time and you'll get the value of velocity. Similarly, if you differentiate velocity with respect to time, you'll get the acceleration value. Now, as you can see over here, so in this right angle triangle O, Q and C, this OQ will be nothing but the adjacent component, so it is R cos theta. Similarly, in this right angle triangle P, Q and C, this QP is the adjacent component, so hypotenuse is L and this angle of obliquity is phi. So this particular Q and P, that distance is nothing but it is L cos phi. Similarly, when the crank is coinciding with inner dead center position, we are having this OC dash as the position of the crank, and that is nothing but the radius R of the crank. Similarly, this C dash and this P dash will be nothing but what? It is the connecting rod. So L is the connecting rod. So this L plus R, so that will be this particular total distance. So this total distance is L plus R. So from this up to this is L plus R. If you subtract this L cos phi and R cos theta from them, then you will get the displacement X of the piston. So we can say that X is equal to L plus R minus into bracket L cos phi plus R cos theta. Now we have to establish the relation between these angles theta and phi. Now angle theta is known as the crank angle and angle phi is known as angle of obliquity. That is nothing but the inclination of the connecting rod with the line of stroke or with the horizontal. So let us try to establish the relation between this phi. Suppose we consider this right angle triangle O, Q and C, then sin theta is equal to opposite side, that is QC, divided by this hypotenuse, that is R. So that we have written over here. So therefore QC is equal to R sin theta. Similarly, if we consider the right angle triangle, that is this P, Q and C, then also this angle of obliquity is phi. So sin phi will be equal to opposite side, that is QC, divided by the hypotenuse, that is L. So therefore we can say that this QC is equal to L sin phi. Now as both these equations, they are representing the same thing, that is QC, we can equate the right hand side of these two equations. So therefore we can say that L sin phi has to be equal to R sin theta. Now transfer this L on the other side. So it is R sin theta divided by L, and this term we can written as sin, we can write it as sin theta divided by L by R, and this L upon R, that is the ratio of length of connecting rod to the crank length, that ratio is known as angle of obliquity. So in this way we can establish the relation between the input angle, that is theta, or crank angle, that is theta, and angle of obliquity, that is phi. Now let us start with our first analysis, that is displacement analysis, and we have seen that x is given by L plus r minus L cos phi plus r cos theta. So let us start with this particular part. So as we have already seen, x is given by L plus r minus, inside the bracket it is L cos phi plus r cos theta. So this we have already seen. Now just simplify this. So this can be written as L minus L cos phi plus r minus r cos theta. Now we can take L common from this term and r common from these two terms. So if you take L common, it will be 1 minus cos phi, and if you take r common, it will be 1 minus cos theta. Now from these two terms, we will take r common. So r is taken throughout common. So it is L upon r into bracket 1 minus cos phi. And as we have taken r common, here it will be only 1 minus cos theta. Now we know that we'll use our basic trigonometry, that is sine square plus cos square is equal to 1. So sine square phi plus cos square phi, that is equal to 1. And from this we'll find out the value of cos square phi, that is nothing but 1 minus sine square. So cos square phi is equal to 1 minus sine square phi, and therefore cos phi will be square root of this particular term, or we can say that it is 1 minus sine square phi raised to 1 by 2. Now apply the binomial theorem over here and neglect the higher term. So we can say that this will be cos phi. Just we'll take this 1 by 2 over here in front of this sine square phi, and then we'll neglect the other terms. So it is 1 minus 1 by 2 sine square phi. So over here, in place of this cos phi, we can substitute this entire value. Now we know that sin phi is sin theta upon n. So let us modify this equation further, and then we'll substitute that particular value. So it is 1 upon 2. So it is sin square phi. So we can write down this as sin square theta divided by n square by substituting sin phi as sin theta upon n over here. Now we can substitute this value of cos phi, that is this entire value over here. So that we have substituted. So you can see over here, in place of this cos phi, it is 1 minus 1 by 2 sin square theta upon n square. And the other part as it is, that is 1 minus cos theta term as it is. Now we know that L upon R is the obliquity ratio. Now open this bracket. So it is 1 minus 1, and minus minus will become plus 1 upon 2 sin square theta upon n square. This term will remain as it is. Now we'll cancel out this plus 1 and minus 1, so that we are left with x is equal to So write down the same terms, and now we'll cancel out one. This is n square and n, so we can cancel out one n also from this. So ultimately what we are getting over here is x is equal to r into bracket sine square theta divided by 2n and this 1 minus cos theta as it is. So this is our first equation, correct, where we have obtained the expression of the displacement of the piston in terms of crank angle theta. Now we have to find out the velocity of the piston, and we know that velocity is nothing but rate of change of displacement, so that is dx by dt, which can also be written as dx by d theta into d theta upon dt. Now d theta upon dt is nothing but rate of change of angular displacement, and that is nothing but the angular velocity of the crank, because theta is the crank angle. Suppose we call this as equation 1. So our first aim is now to find out the value of dx by d theta. So now we'll differentiate x with respect to theta. So this 1 upon 2n is a constant, so it is derivative of sine square theta plus derivative of this particular that is 1 minus cos theta. Now we know that derivative of sine square theta is nothing but 2 sine theta cos theta derivative of 1 will be 0 and derivative of cos theta is minus sine theta. So that we have written over here. So this 2 sine theta cos theta is nothing but sine 2 theta. So 1 upon it is sine 2 theta upon 2n, and this minus minus will become plus. So it is plus sine theta. So this is the expression for dx upon d theta. Now this we can substitute in our equation 1. So equation 1 is given by dx by d theta into omega. So in place of this dx by d theta, we can substitute this value. This entire term we can substitute over here. So value of dx by d theta is r into bracket sine 2 theta upon 2n plus sine theta. So this is the equation which will give us the velocity of piston. So just rearrange the term. So it is r omega into bracket sine 2 theta upon 2n plus sine theta. So this is the expression for velocity of piston. Let us call this as equation 2. Now if we differentiate this velocity with respect to time, then we'll get the acceleration of the piston. So our next task is to find out the acceleration of the piston. So suppose Fp is the acceleration of the piston, so that will be equal to derivative of velocity of piston with respect to time, and this can also be written as dvp by d theta into d theta by dt, and we know that d theta by dt is nothing but omega, so we can say that this is nothing but dvp by d theta as it is, and d theta by dt is omega. So now we have to find out the derivative of this velocity of piston with respect to theta. So we'll consider this equation number 2 for that, and we'll differentiate this equation with respect to theta. So differentiate Vp with respect to theta. So dVp by d theta. So we have to differentiate this equation. R omega is constant, so we have to find out derivative of this term which is present in the bracket. So this is equal to R omega as it is. Now take this derivative sign inside. 1 upon 2n is a constant, so keep it as it is. So we will have derivative of sine 2 theta plus derivative of sine theta. This will be equal to R omega as it is. This 1 upon 2n also as it is. And we know that derivative of sine 2 theta will be cos 2 theta into 2. Now cancel out these two, and derivative of sine theta is cos theta. So we can cancel out these two from the numerator as well as from the denominator. So we are left with dVp by d theta is equal to R omega as it is. Then this is cos 2 theta upon n plus cos theta. Now we can substitute this value in equation 2. So from equation 2 we are having acceleration of piston Fp is given by dVp by d theta into omega. So substitute the value of dVp by d theta, that is cos 2 theta, R omega cos 2 theta upon n plus cos theta, and multiply it by omega. So omega into omega, so that will be R omega square. Fp will be equal to R omega square into bracket cos 2 theta upon n plus cos theta. So this is the expression for displacement, velocity and acceleration of the piston. So let us call this as equation 3. So using these equations we can find out the values of